So even if you're not here, this one doesn't really need to be in any particular context. It can come anywhere. So let's talk about it now. It's 4.4 in our sapling book. L'Hopital's rule. So remember what this is for. L'Hopital's rule is for resolving indeterminacy and limits. So we don't. Before we always did this algebraically, right? We're trying to, we had several different techniques, but this is really easier. This is the way that we generally want to do it. What this tells us here is that if we have a limit of a quotient, it has to be limit of a quotient, so the limit of f of x over g of x, where it's an indeterminate form of the type 0 over 0 or infinity over infinity. It has to be one of those indeterminate types, and there are others that we'll talk about. We may not get to a ton of them today. But if we have something like that, then we can resolve the indeterminacy by just separately differentiating the top and the bottom. Right? Now, you don't differentiate it using the quotient rule. You're taking the derivative of the top divided by the derivative of the bottom. Remember to get that. If you use the quotient rule, it's not going to work. You got the limit of f prime of x over g prime of x is always equal to the limit of f of x over g of x if you're starting off as an indeterminate form. If you're not starting off as an indeterminate form, that's generally not true. Okay, so that's the first step, is you got to verify that. And on the AP test, if you're taking the AP test, you have to actually explicitly state that it's an indeterminate form of one of these types. Okay. So then, how do you use this? Very simple. The step one is you're just going to verify. You're going to check that it's an indeterminate form of one of those two types, a ratio of zeros or infinities, and then you differentiate f and g respectively. And then, if it doesn't work, in other words, not that if it doesn't work, but if it doesn't resolve the indeterminacy, then you just rinse and repeat. You just do it again. You just take as many successive derivatives of the top and the bottom as you need to until you remove the indeterminacy. Okay. So this is just right out of I just copied and pasted this out of our sapling book. So in words, if the limit of a quotient leads to 0 over 0 or infinity over infinity, L'Hopital's rule states that the limit of the quotient equals the limit of the quotient of their derivatives. Okay, and then you can see you can just apply that again, right? Doesn't it make sense that you could just keep applying this over and over? Because if I differentiate the top and the bottom and I get 0 over 0, well then I've got the limit of an indeterminate form. So I would just start over and apply L'Hopital's rule to that, right? Okay. So let's look at a couple examples of this. So what if we had, this is one right out of the book, and then we'll go through a couple together. So if we had something like the limit of tangent x over 6x as x approaches 0. Well, sure enough, if I try to evaluate the top and the bottom, I get 0 over 0, right? So this is an example of one where we can use L'Hopital's rule. And then this tip, you do have to show, you have to verify in writing. You got to write out that it's 0 over 0. Step 2. So then we're going to separately differentiate the top and the bottom. So the derivative of tangent x is secant squared x. The derivative of 6x is 6. And so we end up with, when we differentiate top and bottom, we get a new limit, the limit of secant squared x over 6 as x approaches 0. If I evaluate the top limit, the limit of secant x as x approaches 0 is 1. So secant squared is 1. So we're done. We got 1/6, and that's our answer. And I think I already mentioned this. Yeah, I did already mention all that stuff. Okay, what about one like this? Yeah, it's good. Okay. First step. What do I have to do first?
Just evaluate it.
Evaluate it. Yeah, got to show. See, because it might work, right? But I do get 1 minus 1, so I get 0 over 0, right? 1 minus, or 0 minus 0 over 0. So next step. Differentiate. Now Now I have to drag the limit notation with me the whole time because we haven't evaluated the limit yet, right? So derivative of sine x is minus 1 . Okay. What would you do next? Evaluate the limit. So as x approaches 0, I'm going to get 1 minus 1 over 0. So it's still 0 over 0. Okay. So I got to go again. So the derivative of cosine is negative sine. Derivative of 2x is 2. And now what do I get if I evaluate that? Sine 0, or sine x is, as x approaches 0, is 0. So I get 0 over 2. Is that indeterminate? No. That's an answer, right? So the answer is 0. That's our limit. Okay. What about one like this? As x approaches infinity, what am I going to get there? Infinity over infinity, right? So it's indeterminate. So I'll differentiate top and bottom. I'm going to get 1 over, what's the derivative of e to the x? E to the x. So now that looks, it's no longer indeterminate. What's that look like now? Yeah, 1 over infinity, which is 0. Okay? Oh, I did that one. Okay, what about one like that? Now, that is, okay, so it's indeterminate, right? It's 0 over 0 if I evaluate that at 0. But can you see that if I try to keep taking derivatives of the top and bottom of that mess, it's going to get a little bit ugly, right? Because I've got tangents in there. Tangents give me, secant squared, and then I've got to deal with chain rule from the secant squareds. I've already got a product on the bottom. So it would work, guaranteed it would work, but it could be a heck of a lot of work. So does anybody have maybe a different approach to one like this? Before we jump into L'Hopital's rule, do you see anything that we could do here that might make this a little easier limit to deal with? Like, what have we done in the past with tangents and things like that?
Different trig functions and cancel those.
Yeah, we try to just write them in terms of sines and cosines and see if we can, because those are much easier derivatives to take, right? Sines and cosines are simple derivatives. So we could rewrite this as sine x over cosine x minus sine x all over x squared sine x over cosine x. And then you see that if I could get the same denominator on the top and bottom, those denominators are going to cancel, right? So I could just turn this into sine x cosine x over cosine x, and now I've got a common denominator on the top. And so when I flip and multiply by the bottom, those cosines are going to cancel, right? Let me just show the intermediate step there. So on the top, I've got sine x minus sine x cosine x divided by cosine x all over x squared, x squared sine x over cosine x, right? So I've really got like brackets there and brackets there. And then when I flip and multiply, those are just gonna cancel, aren't they? Okay. And so we could do a little bit more even. So now we've got this is my numerator and that's my denominator. Well, I could factor a sine x out of the top, right? And I'm left with 1 minus cosine x over x squared sine x. And look, I get the sine x's to cancel, that's good. Okay? And so that's a much better derivative to deal with. It's still an indeterminate form, right? I still get 0 over 0, but at least now taking those derivatives is really simple. It's only going to take a couple steps at most. Okay, so if we apply L'Hopital's rule, I'm just going to get the derivative of 1 minus cosine x is just sine x, right? Divided by the derivative of x squared is 2x. Okay, do I even have to go any further here? What's the answer? It's 0 over 0, but can you tell me what the answer to the limit is? I'll give you a hint. Well, it's 1 time, it's 1/2, right? Everybody see that? Because we know this is one of our special limits, special trig limits, right? The limit of sine x over x as x approaches 0 is 1. Do you have to, well, I mean, now you don't even need that special limit anymore because I could just go one more step and take another derivative, right? But you could also stop there. You could recognize that this is equal to 1/2 times 1, which is 1/2. If you wanted to, you know, it wouldn't be a big deal. You could also just say, well, that's equal to the limit of cosine x over 2 as x approaches 0, which is 1/2, either way. Okay. Give me 1 to 5 so far. Is that all good? Okay. Okay. Okay, what about one like this now? So here's an example where if I evaluate that directly, this one does not appear to be, well, it's not immediately in the form 0 over 0 or infinity over infinity, but it's still indeterminate. If I try to evaluate this, let's break this into parts. I've got the x and the log x, right? We know that the limit of a product is equal to the product of the limits. I can just evaluate each of those parts individually, right? So when I evaluate x, I'm going to get, when I evaluate that first factor in the product, I'm going to get 0. 0 plus, I guess. We're approaching from the right. And we have to approach from 0 from the right. How come? Why do we have to there? Look at the functions involved.
You can't take a natural log.
Yeah. The domain of the natural log function is only positive values, right? Positive input values. So then what's this going to be? As we approach 0 from the right, what does log x approach?
1 minus.
No. Think about a natural log function. It goes like that, right? What's the approach? What is it? Negative infinity. There you go. Okay, so 0 times infinity. What's that? That's also indeterminate, right? We don't know. It could be anything. And what does indeterminate form mean? It means that we are required to do more stuff to get an answer. So the approach you take when you have a 0 times an infinity is you have to rewrite that in a way where it either becomes 0 over 0 or infinity over infinity, and then you can apply L'Hopital's rule, right? So in this case, we have two choices. we could write this as the limit of x over the reciprocal of log x. That's one way I could do it, because that would be 0 over 0, right? Or we could do the limit of log x over 1 over x, because that's going to give me infinity over infinity. Anybody see that? Okay. Is there a preference for 0 over 0 or infinity over infinity? No, not really. We just want to pick the one that's easier. It'd be easier to take, if I think about the individual derivatives involved, here I'd be differentiating log x and the derivative of 1 over x. Here I'd be differentiating x, which is simple, but 1 over log x is not so simple, right? 1 over log x is going to require chain rule, and we don't want to use chain rule if we don't have to. So we probably would just avoid, it would work, but we'll avoid that one, and we'll do this one instead. So what's that going to give us? The derivative of log x is what? 1 over x. And the derivative of 1 over x, what's that? That's just x to the minus 1.
Negative x to the negative 2.
Everybody agree? Negative x to the negative 2. So negative 1 over x squared. But we can simplify that. That just becomes the limit of negative x, right? If I flip and multiply by the bottom, negative x as x approaches 0 from the right. So what's our answer? Zero. Right? Do we care about the sign of 0? No, we don't care about the sign of 0. We only needed that when we were taking our limit, right? Okay? Give me 1 to 5 on that one. Okay. Okay, so again, the moral of that story there is, when you've got something of the form 0 times infinity, an indeterminate form, you have to take one of those two and put it on the bottom as a reciprocal. So you either get 0 over 0 or infinity over infinity, and then you just go back to L'Hopital's rule. Okay? Okay, let's look at maybe one more of those. So here's another example where we're going to get okay, so this is one where we're getting infinity times 0. Agreed? Anybody see why? If x approaches infinity, 1 over x approaches 0, right? And the sign of 0 is 0. So I'm getting infinity times 0. Okay, so how should we got to rewrite this as a quotient of either infinities or zeros. So think about our options. You could either write this as the limit of x over 1 over sine of 1 over x. That doesn't look very friendly, right? Or we could write this as the limit of sine 1 over x. I don't know why my board is not working very well here. Over 1 over x as x approaches infinity. So that's going to give me 0 over 0 now, right? So that does fit. We're able to use L'Hopital's rule. This one doesn't look very good. This one we're just going to say no to. Okay, so there's a couple ways we could go with this. We could just straight differentiate this, and that's okay. We could just apply L'Hopital's rule. So the limit, or sorry, what do you guys see something?
No, just
Okay. Anybody see something here? Anybody see a trick? Well, I'm going to show it to you in a
does that do with
second.
an identity? Like you sign it?
Not really. You got an idea? Yeah, you're onto something. you're onto something, but it doesn't quite look like sine x yet, but it almost does. That's really good. What could we do here? Notice that whenever you see this is kind of a trigger in math. If I see the same thing there that I'm seeing as the argument, let me write that so you guys can see what that is. If I'm seeing the argument of my trig function someplace else, like in the denominator, then that's a key that's kind of a trigger for thinking, okay, maybe I could make a variable substitution here. Like we could do something like, let's just say, let's let theta equal 1 over x, if we make that variable substitution then, right? Well, if theta is approaching 1 over x, would you agree that as x approaches infinity, what does theta approach? 0. Okay, 0. But because we're taking a limit, we want to maybe be just slightly more specific. 0 plus, good. Everybody see that? Okay, so that was good thinking, right? Because now we end up with the limit of sine theta over theta as theta approaches 0. And the fact that it's approaching from the right, who cares? It's still approaching 0. That theorem still applies. And so what's our answer? We know that one. What's that one? 1. Yeah, good, right? Okay. Did we have to do that? No, we didn't have to. If you didn't see that, we could have applied L'Hopital's rule, but that's kind of an ugly form, right? I mean, it's eventually. Yeah, I think it's going to work. It's going to work, but it's just going to be harder derivatives to do. Okay, if we just differentiated those independently. Did I just do that? Oh, that's different. Okay. Okay. Oh yeah. Okay, this is different. Right. So what if we try this one? This is a different indeterminate form. So let's first of all let's write down the indeterminate forms that we've even looked at so far. So those are the two that we can apply L'Hopital's rule to, right? We've gotten some other ones. If we have 0 times any flavor of infinity, right? I mean, it could be negative infinity, positive infinity, any flavor of 0 times infinity, we've got to convert that into one of those two forms. Okay, another one that we can run into would be something like anything of the form infinity minus infinity. Infinity minus infinity is indeterminate, and so if possible, we got to turn that into one of the green forms also. Okay, let me ask you this, are these forms indeterminate? No, what's that equal to? 0. Indeterminate? The answer is no. What's it equal? Infinity. Okay. So those we don't have to worry about. But if we get something of the form infinity minus infinity, that could be indeterminate, right? If the infinities were really balanced, that could end up being a finite answer. Okay. All right, so we'll add to this list too, but let's do, for today, we'll just do one of these. So if I try to evaluate this one, sure enough, I get infinity over infinity. Or I get infinity minus infinity, right? Okay. Yeah, I was going to do something tricky with this, but I'm not going to. Okay, so what do we have to do then? We've got to somehow turn this into either 0 over 0 or infinity over infinity. And the way we do that is just algebra, right? We're just going to combine the fractions and see if we can turn this into one quotient that's going to be indeterminate. So we could get a common denominator. Are we about out of time? So if I get a common denominator, I would just multiply this one by sine x over sine x. Multiply this one by x over x. And sure enough, what do we got now? Zero over 0, right? So from there, that wouldn't be very hard to do. Now I could just apply L'Hopital's rule, okay? So really, from there on out, we don't even need to do it. But it's just the trick is you got to get it into one of those forms. When are we out of here? 25? Yep.
How is the 1 over 0 is?
How is it infinity? If x is approaching 0 from the right, think what that's going to be like. I'm going to get things like 1 over 0.00, right? You see what I'm saying? The closer I get to 0, the bigger that fraction becomes. Okay? And we just know, that's when did we use that? We used that when we were way back when we were taking limits and we were dealing with rational functions. We have a theorem that tells us the limit of, here's the theorem we use. The limit of c over x to the r as x approaches 0 is always equal to infinity, right? And we also know the limit of c over x to the r as x approaches plus or minus infinity equals 0. Okay. All right, so I'm going to maybe grab one more example out of here, so maybe we have time for one more. So, well, here's where I want to go with this. And I may not have time to do it today, but the other indeterminate forms that we need to add to our list are these. We could have 1 to the infinity. We could have 0 to the infinity. Or I think we could have infinity to the 0. Yes, we could. This should be 0 to the 0. And that's kind of a weird one. Or infinity to the 0. Yeah. So those are the other indeterminate forms. If we ever get anything of these forms, we have to do something similar. We've got to turn these into quotients and use L'Hopital's rule. You can kind of reason. Now, think what we're really doing here. We're talking about limits, right? If the limits, in the limit, we get something like 1 to the infinity, or it doesn't have to just be 1. It could be anything. It could be any constant to an infinite power. Well, actually, that would just be infinite. Never mind. It's 1 to the infinity. 1 to any power is supposed to be 1, isn't it? Right? But if it's an infinite power, this might not actually be 1. It's just approaching 1, right? So it might be something like 1.00. You see what I'm saying? It might be something slightly more than 1. Something slightly more than 1 approaching an infinite power, all of a sudden that does become indeterminate, right? Because you start to build, you see what I'm saying? I mean, the two are fighting with each other. You've got the tendency of this part of the limit, the base, to go to 1, but you've got the tendency of the exponent to get infinitely big, and the two are clashing, and you just don't know who's going to win. It could end up being infinite, it could end up being 0, or it could end up being anything in between. Same thing here, right? The base is approaching something really big, but the exponent is approaching 0. Well, anything to the 0, we should be 1, shouldn't it, right? That's our 0 power property. But not if the base is infinite, right? This one is just weird. This one is just weird. That's a strange one. We'll look at an example of each of those, but I think we're probably good for today. We're out of here in just a couple minutes, aren't we? All right. L'Hopital's rule is super handy, though. You'll use that every level of calculus. You'll use that one over and over again.
No.
Hey, so I guess one last thought. I mean, just think about, and we'll get to this next time. Think about all three of those. Those are all indeterminate forms that would come from something like a function to a function power, right? How do you think we're going to deal with that? Like, how would we normally deal with something like all three of these? Come from something like, gosh, what is this thing? Some function to a functional power, right? How do we normally deal with that? Like, what if I set it equal to y? No, I can't use chain rule because there is no derivative. We don't have a rule for function to a power that's a function. We can deal with functions to a constant, right? Yes, that's it. You use logarithmic differentiation, don't we? So we got to unlock that. We got to turn the power into a product. Very good. Yep, that's it. That's going to be our strategy. Okay.